Hello, everyone. Can you see my screen? Yep, okay. Any questions or complaints about the quiz? Take that as a no. Okay, any complaints or questions generally? Okay. So we're going to do this one where we're going to use some Venn diagrams to show that B union C minus A is equal to B minus A union C minus A. So to get started, yeah. So to get started, remember you need to have your sets where all of these intersections appear in your drawing. And we're going to do 2. And I'll give you a minute or 2 to do that. Yeah. I mean, we give you half an hour to... I'm responding to chat. There is half an hour to submit the quiz, but did the quiz take longer than an hour? Yeah. Sorry about that. We designed it to take an hour. Do you remember which one you took the longest on? I see. Yeah, so if you're worried about time to prepare your submission, maybe just practice, just doing it again to make sure you can get the time down. Okay. So if you look at the resources page, we we list that you have access to Adobe Acrobat Pro, and it's really easy to combine PDFs in that from images. If you want help with that, you can get help in office hours with that. Okay, I guess probably most people are done, so I'll just start on this. So what should where did everyone start?
I did the union of B and C.
Okay, so probably helps to label these. So the union of B and C would be this portion here. So obviously it includes part of A. If I can draw this correctly. And then We subtract off. We're just going to highlight the portion that doesn't have A in it. So here. So I don't think. Ooh, that's a good question. Someone's asking if we're going to do Venn diagrams on the next quiz. I don't think so. I'll try to think about something to do if the next quiz does have Venn diagrams, I'll think of something to do on that. That's a good question. So we have this portion right here as the left-hand side. And then for the right-hand side, we'll do same thing. So we're going to do B minus A is this portion. And C minus A is this part. And we can see that the union is this. And yeah, so someone's saying OneNote can do the PDF export. I haven't done that, but it might be something you want to look into. We can see that the left-hand side and the right-hand side are equal. So this shows that the identity is true. So the main reason we do Venn diagrams is just so you can have a visual way of seeing these set operations, and maybe build your intuition about it. Maybe check your work once you've done something. Yep. Any questions on this? I'm going to say no. So I think this one we're going to do an element-wise proof. So to refresh your memory, we're going to show if we have an element X in A union B intersect C, then we need to show that X is in A union B intersect A union C. So I'll just get started a little on this. So if we take apart what X in A union B intersect C means, then it means X is in A or X is in B intersect C. I'll give you a couple minutes to work on this on your own. Yeah, so if you're having trouble with the time it takes to prepare your submission, you can come to office hours and we can show you how we put them together quickly. Okay, so I'm gonna guess most people probably have finished. So where should I start? Nothing. Okay, so if x is in A, we know that it's true that x is in A or x is in B. This is a true statement, right? Because this is true. And this means that x is in A union B. Similarly, we know that x is in A or x is in C. And this means that x is in A union C. Since both of these are true, we can say that x is in A union B intersect A union C. Any questions on that? Okay, and so for the second
I have a question.
Yeah.
Sorry. So the process is you look at if x is in A, and then you look at what we're trying to the
Yeah.
implication, and since x is in A, it's also in A or B.
Yeah,
And
exactly.
That's the logic, and then
Yeah, so
okay.
Yeah, so we're just trying to show that that it's in the right-hand side on this one, right?
Yeah, and then the next line is you proving it's in the right-hand side.
Yeah.
Over.
So we're trying to
union.
Yeah, we're trying to
C.
construct an argument to say that it's in what's on the right-hand side.
Okay.
So, yeah.
I was just okay, thank you.
Yep. Yeah, so we noted that there were two cases because we're dealing with a union. So we know that x is in B intersect C, and the definition of this is that x is in B and x is in C. And so if we go from this one, we know that x is in B or x is in A. And this shows that x is in A union B. And this one means that x is in C or x is in A. And this means that x is in A union C. So we have both of these together, and this means that x is in A union B intersect A union C. So this is an element-wise proof of the statement. Any questions on that?
Can we use the other logical operators for or and here, like the up caret and the down caret and stuff?
Yeah, you can use those. So the reason I didn't do that here is because if I don't make this wedge shape, if I do it like that, it kind of looks like an intersection. So that's why I'm using and or as words. Anything else?
So if I understand, what makes element-wise proof different from other proofs is that we declare that x's exist in one of these sets, and then we try to prove x exists in all the sets some way.
Yeah. So So you're showing if X is in A, then X is in B. And this shows, red is the worst color to draw on there. This shows that A is a subset of B, right? If you want to show that the sets A and B equal each other, you also have to do X is in B implies X is in A. Can you see this?
Yeah, kind of, yeah. The blue works out.
The blue isn't the best color, but yeah, so if you're showing equality using element-wise, you have to show both ways. And that shows that A is a subset of B and B is a subset of A, which means that they're equal to each other. Yep. Good
So
question.
you have to prove both ways.
Yep. Yeah, we only have to do one way because this is just containment. Good question. Okay, that's just work. Okay, so we're going to be doing this manipulations to show that A union A complement intersect with B is equal to A union B. I'll give you a couple minutes to work on that on your own. Looks like most people are done. So what should I do to get started here?
Distributive.
Yeah, so let's apply the distributive rule, and we're going to use this one. So we're going to get A union A complement intersect A union B. That's by the distributive property. And what should I do next?
Negation.
Negation, and we're going to apply negation to A union A complement. And that gives us the universal set. I mean, A prime, if you know what you're talking about, it's fine, but most people are going to say A complement, but I mean, yeah, I don't, you're not going to get graded on that, so should be fine. And that was by negation. And then what I marked people down for on the quiz. What should I do next?
Identity.
Yes. So if we look at identity,
Commutative.
the universal set is on the right side. Yeah. So we need to do the commutative rule. So we get A union B intersect with the universal set, and that's by commutative. And then finally, we can apply identity. So we have the universal set here, which means we just get the left portion, A union B, that's by identity. Why though? I'm not sure what you mean. Yeah, so we were just doing that because of you need to do syntactic matching on these things. So, you could derive a second identity rule that the universal set universal set intersect A is equal to A, but you need to derive this rule from these two rules together. I don't think on the next quiz we're going to be doing. We're going to mark you down for that though. So I don't know. I kind of wish we had done had the second rule here, but that's what the quiz was. Any questions on this? Yeah, looks good. The next page is blank. Okay. Okay, so this is going to be another element-wise proof. So I'll just write down some stuff to get started. So we're going to have, so I'm going to call this A and B and this C. So we have X is an A intersect B, and we're going to show that X is in C. And I'm going to write, so just to get a little more. So we know that X equals N squared minus 1 for some N in Z. And X equals 2K for some K in integer K. And what we want to show at the very end is that X equals 4M for some integer M. I'll give you maybe 3 minutes to do this. I'll give you another minute because it looks like most people are still working. Okay, so if someone solved it and wants to tell me how they did it. Or not. Okay. So multiply A and B. I'm not sure what you mean. You mean like put B in A? Ah, isn't intersection the same as multiplication? Yeah, so that's on Boolean algebra. So we write like A intersect B is, oops, A. We use this multiplication here, but yeah. Yeah, we got another one. It said maybe substitute x in for n. That doesn't quite work because n is a different integer than k. Okay, so this is how I did it. So if we look here, we can write this as x equals n plus 1 times n minus 1. And there's two cases here. So if n is odd, then we can write n equals 2 L plus 1. L is an integer. So this means that x equals 2 L plus 2 if I just combine those immediately. And 2L, so we have a plus 1 and a minus 1 here. And so we can see that this is equal to 2 times L plus 1 times 2L. And that's equal to 4 L plus 1 times L. Set A and B equal to each other. I'm not, so like this. Yeah, it doesn't quite Oh, you mean like, I see what you mean. We'll be doing that. So if x was even, n was even, we would do, we'd do the same thing, but we would find that we have an even times an odd number. We have an even plus an odd number is odd, an even minus an odd number is odd, and this whole product would be odd. So we know that n can't be even because we'd have odd times odd. And so this means this doesn't happen. So now we look here and we know that n plus 1 times n minus 1 equals 2k. And oh no, I didn't show this here. Sorry. We know that because x equals 2k, and these two are equal to each other, that n can't be even from up here, because that would mean that x is odd, and this makes it even. And we showed here that there's some integer L such that this is 4L plus 1 times L that's equal to 2k. So right here, we've shown that x is equal to some integer times x by closure. Some integer times 4. And this means that we can write x is equal to 4m, where m equals L plus 1 times L. And then this shows that x is in C. And that demonstrates what we're trying to prove. Any questions on that?
Do we need to address if n is even like you did, or is that just something that like did you need to say that n can't be even?
Yeah, so we need to say that n can't be even because it makes an odd times an odd number, right? From here. And the reason it can't be even is because we know that x is even. Does that make sense? Which means that we're in this case where we have an even times an even number to get 4.
Yeah. And that's just because A intersects B, and so that's why you set them equal to each other, right?
Yeah, because we know that by the definition of intersection that x equals n squared minus 1 and x equals 2k, right?
Yeah.
And so since x equals both of these things, that's why we can set them equal, right? That's the definition. Good question. And 7 raised her hand.
It's Savine.
Savine?
Yeah.
Sorry.
It's okay. Everyone does it. So is this just proving by cases then?
Yeah, there is a proof by case here with this even odd, right?
So like if x is odd, or n is odd?
Yeah, n is odd.
Oh, so the first case is if n is odd, and then the second case is
N is even.
Oh, okay.
Yeah, and I just was arguing with this x equals 2k that that it's even. So it can't be the case that n is even. Good question. Jacob?
Yeah. So on here, did you show why n was odd times odd when it was even, or did you just like tell us?
I just told that mostly to save time.
Okay.
Yeah. So we would have 2 L plus 1 times 2 L minus 1. And then if you work this out, you'd get 4L squared. L squared minus 1, that's odd, right? Good question. Anything else?
So if I understand, like the end goal, the final answer is to prove or to find a case where M equals N, which equals K in each situation. But is that right?
Yeah, so what we're trying to show is that X's can be written as 4M, right? Because we're trying to show that this X that's in the left-hand side is part of the right-hand side. So I'm not quite sure if that's what you're asking.
Okay, so maybe the end goal is just to prove how X equals M then.
Yes, show how X equals 4M. Yep.
I have another question. So after you learned that N can't be even for when you solved for N squared minus 1, did you only plug in an odd number for 2K because you knew that it couldn't be even now?
Plug in an odd number for 2K. No, this is just for all integers, right? Because 2K is even. So we need this to be even.
But did you when you plug in for 2K to like solve it, can you not use an even number now because in A it got you an odd number? Like, can you not use even for the second case because the first one didn't work out?
Yeah, so we're not using this N is even case because
it didn't work for the first one.
Yeah, this won't work over here.
Okay,
This
gotcha.
is an odd number. You know, we can't have an odd number equaling an even number. Let's see, 10 minutes left. Yeah, it should be fine. Anything else? Okay. So for this one, we're going to be doing the Boolean algebra thing. These are written in set notation, but you can easily convert them. So just a refresher, A intersect B, this goes to A times B, A union B goes to A plus B, and A complement goes to A complement prime if you want. I think that should be enough. So I'll give you a minute to work on this. Okay, does anyone have a clue to where we should start? Yeah, okay, so I'm going to start by noticing that we have this subtraction. Yeah, De Morgan law is, wait, are you looking ahead? So we have this subtraction. We're going to need to use this complement and negation. Oh, okay, I see I see you're trying to prove this. We're just going to rewrite this formula. So we're going to use this complement and negation to rewrite the left-hand side. So this is equal to A intersect B intersect the complement of B intersect C. And this is by the complement and negation rule. And likewise for the right-hand side, we're going to write A intersect B minus C. That's the same as A intersect B intersect the complement of C. That good? And now we can use these rewriting things here. So we're going to get A times B times B times C complement. And we're going to say that's equal to A times B times C complement. Is that good? This one should be easy, mostly as a lead into the next one. So on this one, we're going to show, where do we use complement negation? So right here we have this subtraction. Oh yeah, we used it here. Yeah, good question. So we're going to be using these set rules to do this Boolean algebra calculation. So what we want to do is show that if AB equals A, then A complement plus B equals 1. And some extra rules here. We need that 0 is equal to the empty set, and 1 is equal to the universal set. And I'll rewrite the other ones. A times B. That's A intersect B. So these rules let you convert the these rules into Boolean algebra operations. I'll give you a minute. I guess we're running out of time. Okay, does anyone have a clue to where to start? No clue. Okay, so we're going to start by writing this left-hand side. B is the same as A. Yeah, that's what that might be. Yeah, so that's actually not quite true because we effectively have A intersect B is equal to A. B could be a superset of A without having, it could be distinct from A. Good question. So we start with A complement plus B, and we can use the fact we were given to rewrite this A here. So we get A times B complement plus B. And that's because we were given that. Because A equals A times B. And then, in the interest of time, I'll just work through this. We apply De Morgan's rule, and we get A complement plus B complement plus B. That's by De Morgan's. And that's equal to A complement plus B complement plus B. And that's associative. And that is equal to, I think I'm going to have to apply commutative. Yep, because I'm trying to apply negation here. So we get A complement plus B plus B complement. That's commutative. And that's equal to A complement plus 1. And this is by negation. And then I'm going to apply identity. No, it's not identity. It's is it identity? Yeah, it's universal bound. And that equals 1 by universal bound. Any questions on that? Yeah, I guess that takes us to time. So I guess you're going to have to work on this on your own. So this is going to have to be element-wise. And it's going to be similar to that one we did with the n squared minus 1 and 2k thing. What you're going to need to show is that A intersect B is empty. A intersect C is empty. And B intersect C is empty. And so this is because this is a partition. And we're also going to need to show that A union B union C is equal to this. So to do this, we need to show that for every integer n, n is in A, or n is in B, or n is in C. And we're going to need to show that the elements of A can't be rewritten as elements of B. Elements of A can't be written as elements of C. And actually, if you look here, that's pretty easy because we can see that the elements of A are even, but the elements of C and B are odd. So we know these two pretty quickly. Any questions before we wrap up? And I believe we post the solutions to this, so you can look at that. And if you have questions, you can come to office hours. I will be posting this scribble on Canvas, so you can look at that. We don't post solutions to this. Interesting. I see. I'll finish the solution and okay, maybe we do have solutions posted. Is it really 7? Okay, I guess we're getting to, oh yeah. Thank you. Stop.
Thank you.